Hello, everybody, and welcome to our 2021 Taste of Science Indianapolis virtual event. Ironically, we have some nice bossa nova jazz music going when, if you are local here to Indiana, it has been snowing. Yes, snowing in the end of April in the year of our Lord 2021. Who knows what will happen, but I know tonight we will be enjoying a wonderful evening with some fantastic guest speakers talking about everything to do with the cell because you know what? It's a pandemic. Let's take a selfie. For those of you who are new to the Taste of Science Festival, Taste of Science is run by the nonprofit science outreach organization, Scientists Incorporated, formerly known as Pint of Science. We're a passionate group of volunteers dedicated to bringing scientists outside of the lab to explain their work in plain, understandable English to an interested audience, which is you guys. this isn't just happening in Indianapolis. This is an event that's happening all across the country in cities like New York, Houston, Philadelphia, and in a much sunnier place, Tampa. If you would like to learn more about this year's festival and upcoming events, head to tasteofscience.org and bring a beer, bring a lunch. We'll be hosting events all week through this week and next week. Um, but I got to tell you, the Indianapolis team, we do not work alone. It takes a Midwestern village to put on an event like this. We're proud and happy to partner with our friends at Central Indiana Science Outreach, which you can find on Instagram, Twitter, and Facebook as CINSO, CINSO, and our friends at Indiana Sciences, who've helped us put this event together in years past and today. If you're interested in local science nonprofit outreach work, you can find Indiana Sciences on Facebook, Instagram, and Twitter, and you can even find them live streaming on Twitch, especially on Tuesday evenings with their book, Booze and Brains, a book club, which is now virtual. So you don't even have to be in Indianapolis to enjoy some of our wonderful book clubs. In addition, Indiana Sciences is participating in the City Nature Challenge, which is not just something happening in Indianapolis, but could be happening at a city near you. This is one of the largest citizen science projects in the country and will be taking place next week, where cities across the world are competing to document the most urban biodiversity. Do you like bird watching? Do you like taking hikes? Maybe the weather will be nice next week and not be snowing in the middle of spring. If so, we encourage you to go to indianasciences.org/CNC-2021, or just Google Indiana Sciences and go to the website, and you'll find it there. Just participate in this wonderful activity and get outdoors safely. Obviously, distance and wear your mask, but something fun to do in the city, wherever you are. It's our collaboration with these local science outreach groups that allows us the freedom and opportunity to highlight some of the most incredible scientists and scholars here in Indy. We're excited to use this virtual platform to share some of the best Indianapolis has with you all, wherever you may be. Now, today's event is all about the cell. We know that mitochondria is the powerhouse of the cell, and there are hundreds of different types of cells that all do different things, and they work together to make us, us. Cells are like living Legos. We can put them in a dish or build them up into these 3D shapes, and we use them to study all sorts of diseases and test new drugs to find cures for some of the worst diseases. But when we use cells from humans, it gets complicated. How do we use these cells respectfully and respect the patient and the donor while pursuing scientific study? And that is equally as important as the research itself. And that's what our discussion is going to be about today. We will first hear from 3 of our guest speakers, and we'll follow up with a Q&A panel where you can ask questions and we can really dive maybe a little deeper into the topic of cells, cell research, and ethical research using human cells. So I'd like to introduce our first speaker, Dr. Pei Chao Tang, who was a former researcher here at the University IU School of Medicine here in Indiana, but is now enjoying a wonderful sunny spring in Miami at the University of Miami, which is my alma mater, so I have to give a go Canes. I'm a Hoosier at heart, I promise. I've had my pork tenderloin, y'all. We are a Hoosier family, and we are welcoming Dr. Pei Chao among them. Pei Chao is going to introduce us to the wonderful world of cell science and demonstrate some of the ways she uses cells as Legos to answer some really tough questions. Dr. Pei Chao, the floor is yours.
Okay, let me start my screen. So thanks, Allison, for the very nice introduction. So as you know, I used to work in Indiana University when I started my stem cell research, and I kind of miss the beautiful summer there. Although the winter snow, I'm not jealous about that. But it's my pleasure to share my research using stem cell in the inner ear research with you today. So we'd like to ask first, what is stem cell? So stem cell is a very unique type of cell that could be differentiated into many different cell types, such as blood cell, muscle cell, the epithelium in your intestine, neuron, etc. So stem cell can be collected from many sources. Also, of course, a lot of people might heard about like from baby fetus. It just have like scary feeling about stem cell. However, there is a more common way we will obtain stem cell from such like bone marrow, or we can even induce them from the blood cell we collected from people. So now we talk about briefly introduce what stem cell. Now I'm going to give you another important part of this talk, which is the ear. So you can see in the ear, human ear contains the outer, middle, and the inner ear. And in the inner ear, there are two very important sensory systems within the inner ear. It's the vestibular organ, which is responsible for balance and the motion sensing. And another is the cochlea, which is responsible for hearing. And then both systems contain a very unique cell type, which is called hair cell. As you can see, they have little hair on top of their cell, which can transduce the mechanical waves, such as the motion of your head or sound wave, into the neuronal signal. And such signal will be passed to your brain by a very specific nerve system. The defect in both the hair cell and their associated neuron will cause inner ear disorders such as hearing loss, imbalance, or vertigo, that kind of symptom. But it is very challenging for us to study the inner ear in the live animal, not even mention human, because it's very difficult to almost impossible to have access to these organs without causing any extra damage, unnecessary damage. So such limitations have prevented us to progress our understanding in the inner ear and how to combat the inner ear disorder. However, stem cell, on the other hand, is very relatively easy to be manipulated in the laboratory setup. So these stem cell-based systems can provide an alternative platform for the inner ear research. And here we kind of sum up, there are three major culture systems. The first two are the two-dimensional culture system. They differentiate the stem cell into optic epithelial progenitor and optic neuronal genitor, followed by specific cell types. And then the third type is the three-dimensional culture. So we form the cell into a tiny ball, and this tiny ball contains a lot of different cell types. We call them organoids. And organoid is known to be better mimic the real life tissue and the formation of organs. And the rest of talk will focus on this organoid system because this is what I have been using since I joined the IU. And this organoid system is really new, and it started from the research group in Indiana University. So it's very promising. And they published their finding of this system in human and mouse stem cell system. And then they published their data in very prestigious journals and attract so much attention. So it's like a lot of people have high hope about this organoid system to progress our understanding in inner ear field. So what can we do with this inner ear organoid system? So in combination with a lot of other technologies, such like genomic editing with CRISPR, I believe some people might have heard about it. So we can use this system to understand the mechanisms underlying the development or disease modeling. And we can even use this system to generate a lot of tissue for the drug screening. And with the knowledge learning from those processes, we can even obtain the patient-specific stem cell to develop cell therapy or personalized medicine. So there is a lot of potential there, but we need to start from somewhere. So where we started. So the first study we have done to use this stem cell organoid system in more applicable form is to modeling the deafness related gene. And as you can see, this kind of organoid, they contain very beautiful red stem hair cells surrounded by the green cell, and then they represent what's the unique hair cell inside of our ear. And we targeted a human deafness related gene, TMPR3, because this gene is important because they cause prelingual and then postlingual deafness. And what we do here is we use this stem cell-based culture system to understand what's the pathological phenotype of mutation in these important genes. But in addition, we also parallelly work with the animal model, since we want to make sure like this novel system can really catch what's really happened in the animal. And it's very encouraging that the mutating the TMPR3 protein resulted in the same pathological outcome in both sick cell derived culture inner organoid system and the mouse inner ear. So this means this novel stem cell-based system can catch the phenomena really occur in the live animal, and we can use this system to understand the mammalian genetic abnormality and then what's really associated with the abnormality, like pathology, and then what the function involved in this thing. So what else we can do? Now we are happy to see like this system really can represent what we want to know about the live animal. And then now my current research after I moved to Miami, my research focuses on the inner ear development, because most of our knowledge in development, especially in inner ear, is from the non-mammalian model. So with this stem cell-based system, we can study development of mammalian inner ear, and then more excitingly, we can obtain the human-derived stem cell and then study human development. So now the question what I'm trying to answer is to model and then elucidate the development of the human ear. And as you can see, we can grow this organoid, and then they contain the optic vesicle, which is the part of process of development of inner ear, and ultimately we will have beautiful organoid containing many specific hair cells, which we are very interested in. And the more exciting thing is that single cell RNA-seq, which is a cutting-edge technology, it can be easily incorporated into stem cell work. And then using this single cell sequencing knowledge, we can analyze tens to millions cells at once and know how cells transform, how they change over time. So this kind of work can allow us to answer some really fundamental questions, such as reconstruct the lineage tree for the cell, and then understand how they grow, and then how we really, from a single cell embryo toward a whole ear on your face, by your face. But on the other hand, from those knowledge, we also can start seeking solutions to tackle the congenital inner ear disorder. And the more exciting thing is this organoid system is not only contain the cell from in the inner ear, it also exhibits the potential to study other craniosensory systems, such as lens, smell organ, or how your face moves. So hopefully I have shown you enough and then convinced you that this stem cell-based research is very exciting, and then we can do so much with stem cell system, but even though now I'm just showing you the very beginning of this role. So, well, thank you for your attention. And I want to also thank you, like, of course, the Nelson Lab at Indiana University and all the researchers at Indiana University. And then the group I'm working with at Miami now and all the funding agent. As you can see, Indiana CTSI also very helpful and supportive of doing research. So thank you so much. And then I guess later we will have Q&A and I will be more than happy to give more detail or answer any questions.
Thank you so much. And thank you for showing off those beautiful pictures. I had no idea. I mean, maybe I just don't know what an inner ear looks like, but those pictures of the organoids with all the, just beautiful pictures. And that's so impressive to think that this technology of, developing this inner ear organoid has only come around in the last few years. I didn't realize ears were so complex.
Yeah, ear is like very, very beautiful. And then the cell within it is just like amazing. Everybody should Google hair cell, and then you will just like know why I dive into this research, just because cells are amazing and they're beautiful.
Yeah, it brings a new meaning to cell service, because ears and cell phone, that was really bad. We're trying. Thank you so much, Pei Chao. I look forward to hearing from you in the Q&A, because I have a feeling we're going to have a lot of stem cell questions, because they are definitely a special type of cell, and I feel like I learned a lot about the ear, something I take for granted. I'm taking it for granted right now, and I don't even realize it. Thank you so much. So moving from stem cells, we're going to get into a different type of cell and a different type of cell research. Now, if you are a Hoosier, a real Hoosier, and you are living in Indianapolis, you've probably read about our next speaker and maybe not even realized it. Her and her research group are really local heroes. Dr. Karen Pollock is an associate professor of pediatrics at the IU School of Medicine. She's the basic science leader at the Brain Tumor Working Group and is co-director of the Signature Center for Brain and Neurological Tumors. You probably know her best for her group's work with Tyler Trent and his cells. And Dr. Pollock is going to take it away and give us a wonderful, I've heard her speak before, a fantastic talk about her translational research with cells. So Dr. Pollock, take it away.
Well, thank you so much for that kind introduction. It's just wonderful to be here with everyone today. And I followed some of the work at Indiana University on the ear organoids and actually reviewed a couple of your internal grants, I think. And it's just a beautiful work. It really is. So what I'm going to talk to you briefly today is really about Tyler Trent and his legacy and how it fits into the research program at IU. See if it's gonna let me, it's not letting me advance my slide. Let's see. We go that way. Huh. Let me go out and then try again. Not sure why I was doing that. I'll go over this one. Let's see. Can you all see that? Okay, this one's advancing. So where I want to start here first is to really focus a little bit on a theme that I think we're going to pick up on the third talk, and it has to do with regulation of research. And the Tyler Trent case is a pretty unique case in that regard, in that the vast majority of the patients that we work with, we never know who they are over in the research side. But occasionally we will have a patient that comes along, and Tyler was, he was of age. He was, 18 plus when we first met him. And so as I'll talk through our pipeline here, I'll bring up Tyler's models as an example. But clearly when Tyler came to Riley Hospital, this young man had so much going for him, just like all the kids that come to Riley. Unfortunately, the type of tumor that Tyler had is a solid tumor in the bone, and it's called osteosarcoma. And unfortunately, January 1 of 2019, he succumbed to this disease. But Tyler has really left a legacy, not only in the state of Indiana, but really nationally, in terms of being such a strong advocate for research in general and helping raise dollars for cancer research. And so what I'm going to do now is give you a brief glimpse into what we call our pediatric precision genomics pipeline. And this is really centers on what some of you all may have heard out in the literature, out in the news, called personalized medicine or precision medicine. And basically what this means is that children, when they come to Raleigh Hospital, many of them will have their cancers sequenced or have a molecular profile done. And what this does is it gives us at least some clues onto very customized types of treatments that we may be able to use for that patient. And there's all kinds of markers or biomarkers, as we call them, again, that may supply these clues on what type of therapy we should use for which patient. And so Tyler was actually entered into this program and for a while did quite well on the program. Just as some brief background with the clinical program that we work closely with, typically in Indiana, there's about 370 cancer diagnoses per year, and that's ages from 0 to 19 years of age. About 30 to 40% are solid tumors. Some of them you'll be able to tell right away whether they're really high risk. Some of the children, of course, go on through frontline therapy and they just do great. Others will have a disease relapse, such as unfortunately that Tyler did, and then you would go on to a second line therapy. But this program, again, is designed to look at kids right up front and also later if unfortunately they relapse. And so the objective of our program really is connecting the clinic with the research lab, and then information that we gain from the research lab, some of it at the proper point in time, then can go back to the clinic to hopefully improve quality of life and also better outcomes for these patients. And so this is the world that my group works in. We work in a world where we engage with our physicians, our oncology team that's led by Dr. Jamie Renbarger at Riley. We develop hypotheses working with the clinical team, and then we have lab investigations, which also generate many more hypotheses that we can test. And we also integrate our local data with what's known in the public domain. There are a number, as many of you may know, public data sites we can go to integrate our data in with larger data sets. And this is very important for pediatric cancers because fortunately, pediatric cancers are very rare. Typically, there is only about 3 to 4 osteosarcoma cases per 1 million people. So it is very rare. So a little information on what we do. So working with a clinical oncologist, we have what we call a patient-derived xenograft pipeline at Raleigh Hospital. We work with the clinical staff and the coordinators. There's emails that go around on a weekly basis. And some of these kids, when they come in, again, all de-identified except for an occasional case like Tyler, who's given us permission to talk about him, and his family's given us permission. But these cases come in. They come in with 2 wonderful people I work with, Sholay and Reza, and then they coordinate the generation of tumor models in mice from some of these human tumors that we see. And what I want to emphasize on this slide is that you can see there's a whole team of folks that are involved in this research. We have the clinical, we have our biobanking people that then coordinate this with the Cancer Center's preclinical modeling and therapeutics core, where we then can take these very small, precious pieces of tissue, implant them into an immunodeficient mouse model where it doesn't have an immune system, so the human tumors can grow. And then we can expand these samples up, and then we can analyze them and begin to address new types of therapeutic options for these particular tumors, which I'll give you a couple examples of. So these are some of the folks that work in my lab. And what we're going to do now is talk about 3 of the models that we actually developed from Tyler Trent's tumor sample. And one of them is called a spheroid or a sarcosphere model that we work in. And we also have a mouse model. So just briefly as background, osteosarcoma is actually the most common pediatric or adolescent bone cancer. It has a bimodal incidence, meaning in that early growth phase where these kids, and particularly males, are having these very rapid growth spurts, they're a little more susceptible at that point. If the disease is caught localized, 5-year survival rates are actually really good, greater than 70%. But if by chance the disease has already metastasized to other organs, the chances of surviving 5 years is really 0 to 30%. And there's one common feature of osteosarcoma that we are working on that we think is one of the better therapeutic approaches that's really still kind of in that phase of taking the models, testing them, and is not completely over to the clinic yet. And this has to do with the chromosomal instability that you find in these tumors. These tumors are constantly changing their DNA and being kind of sneaky, finding ways to survive, say in the lung, or to survive in the liver or the bone or where have you. So they're actually very sneaky tumors because of this genome instability that they have. So this is a schema actually of Tyler's treatment history. Again, he gave full permission for us to show this information. And what you can see is that extensive types of therapies that go on with these young folks when they have a metastatic osteosarcoma. His disease was actually diagnosed back in July of 2014, and he was put on what we call a frontline therapy. And for a while, he did very well on that therapy. Unfortunately, in May of 2017, he came back and he had relapsed and had to undergo surgery. And what you can see right here is that in this particular case, there was sufficient tissue, tumor tissue, for there to be 2 donations that Tyler made to the Pediatric Precision Genomics program. One sample was from May of 2017, and then another was just a couple of months later in early August of 2017. And we were able to take these samples, implant them very quickly into our mouse models, and then actually generate a substantial amount of tumor tissue that we are still studying today. We constantly have many of these PDX or patient-derived xenograft models going. This program actually started in 2016. So when Tyler first was diagnosed, we did not have the Pediatric Precision Genomics program. He actually came in about a year after the program started. But to date, we've actually generated 32 different PDX or patient-derived xenograft models from these very special kids that are seen at Riley. And then what you can see across here are decisions that the clinical oncologists made based on lots of things we found out about the molecular profile of Tyler's tumor. And there were some different types of small molecule inhibitors that were tried. But unfortunately, in this type of situation, his disease had really progressed. And what Riley is doing now, based on research that we and others are doing, is they want to be able to use some of these more experimental therapies up front, maybe when the disease burden is going to be a lot lower. And so in terms of research, here's Tyler's legacy for the state of Indiana and Riley Hospital. All of these are models that were developed from the tumor samples that he donated. We first have what we call a 2D monolayer. And this is the type of culture that I'm sure many of you've seen that grows in flask or on Petri dishes and things like that. And it still serves a great purpose, but we know this is not how tumors really grow. And so what we're always trying to do is to simulate what may be happening in the patient, make it as real as possible so we know that the data we're getting from our research is long-term going to be beneficial to patients. And so another model we work in is a 3D sarcosphere model. We call them mini tumors. And this is another way that we can go and test drugs and understand how these tumors may respond. But certainly the best model in terms of simulating the patient is to actually take these cells and put it in the bone of the animal, and then use this as a model to test novel therapeutic approaches. And so this is just one example of some data where this was from one of Tyler's models, where we take the mice and we actually implant similarly sized chunks of the tumor into the mice. Again, highly regulated work. There is an entire committee at IU on anything that you do with animals has to be submitted. It's called our IACUC committee, and it has to be submitted and it has to be approved by this committee before you can do it. So again, on the clinical side, we have lots of institutional review board regulation. And then on the research side, we have animal care regulation that we use. But here's an example of some of the initial results we got with Tyler's model. So it took us a good year to get the model, to expand it, to understand as much as we could about these very complex molecular signatures that osteosarcoma patients have. But based on that, we developed a pretty novel type of therapeutic approach where we tried to exacerbate or increase the genome stability in these tumors to the point where you actually kill the cells. And that's what we did here. And we work with what we call a bromodomain check-1 combination therapy. And the novelty here was both of these inhibitors have been looked at before, but no one had combined them in this type of approach. And so these are groups of mice that have been implanted with a tumor, and then we have treatments. We have a single drug treatment or we have the double drug treatment. And then we monitor the volume of the tumors over time. And so what you can see quite clearly here is that mice, this is a group of mice that got a vehicle or control. The red groups got a CHEK1 inhibitor and the purple groups got a bromodomain inhibitor. But what you can see quite nicely is that while the mice were kept on the dual combination therapy, the tumor growth halted. It just stayed in place. So that's exciting, but just as important is what is the health of this animal? One of the biggest dose limiting, problems that patients have is that these drugs can affect normal tissues in their body. And so we spend a lot of time looking at normal tissue toxicity to make sure things are okay in the animal. So body weight is just a very general way we look at it. We also have clinical observations where we look to see if the mice are not eating as much, are they not grooming themselves properly, or they have less activity. These are clinical observations we follow. We also check the bone marrow cellularity. Many of you may know the bone marrow is very susceptible to drugs in terms of just very sensitive to them. And then we do a lot of histology with our pathology group to look at the integrity or the organs as well. And so on the final slide here, where are we now with these models? So out of the PDXs models that we've developed, we actually have 13 osteosarcoma models from kids that have been seen at Riley. Some of the kids are still alive and doing well. Some of them have relapsed and haven't done so well. So we have very different types of molecular signatures that we can study in the lab. And the thing that is really key here in terms of making these types of models, from kids that are seen in your local neighborhood, basically, is that we have such a great pipeline with the oncologist. We can discuss with them, well, what's going on with this patient now? What type of treatment have they had? How are they responding to it? And then we can simulate these things in these mouse models. So a big area of focus in the lab these days is actually, again, this is the Trent model. You can see once we take it off therapy, the tumor starts coming back again. So we're doing a lot of experiments now to look at tumor adaptation to therapy and look at how we can design a second phase of therapy that would be well tolerated and that will target some new vulnerabilities in those tumors. And these are some of the omics approaches that we're using for this, what we feel is just very exciting work. And so with that, I'll thank you for your interest in what we do. This is certainly a big team that works on various aspects of this work. And I wish to thank all of our funding organizations, as well as the Raleigh Children's Hospital. And also can never thank enough Tyler Trent and his wonderful family, who I know very well. who have continued, his family continue to be such strong advocates for cancer research locally as well as nationally. So thank you very much for your attention, and I'll look forward to answering questions later.
Thank you, Dr. Pollock. It's incredible the work that you and your group do, and every time I see it, I'm always amazed. And I will say I am a cachexia researcher, so it's always good to see that you're tracking body weight, tracking cachexia, because it's always something that we're worried
Very
about.
important area. Yes, absolutely.
Especially in the pediatrics, we're so worried about development. And
absolutely.
That's wonderful to hear that your group has made such incredible progress in such a complex and really, for many families, terrifying time and disease. And that's incredible, the way you're able to use human cells in a mouse model to do that. I have a feeling you're going to get some questions about that, so I'd be ready.
Okay. Yes. Yeah, we've really found too that the families that are involved in this, it does give them some hope. It gives them some purpose on something that they can, help with as we develop these new therapies. So thank you.
Yeah, and what a great segue too into our next speaker. So obviously the dealing with pediatric cases is maybe a little different, but when we're talking about when we're trying to do research on diseases, of course we want to study the human disease because we want to cure the human. So we want to use human cells and human samples. But you can't just walk up to somebody at like a Walmart and ask for a blood sample. That would be really weird. And also I can't stalk you or I don't need your social security number to know what your blood glucose level is, or, if to take some cells off to the lab like a mad scientist and do crazy experiments and make clones. It's not really how human research works. There's a lot of consent, which will be, I think, the key word as we move into our next speaker's talk, talking about human research. So I will introduce Amy Waltz, who's an associate director at the Research Integrity Office at IU and a legal expert. Amy is going to take us from one bench to the other, hopefully one we don't want to find ourselves behind, and talk us through some of the regulation and legal changes that have been made concerning human research. Without experts like Amy, our other speakers and us couldn't do the research that we do. So we thank you for your work, Amy, and we look forward to hearing from you.
Thanks a lot, Allison. I really appreciate that. I don't know if I would call myself a legal expert, but that's great. What I do is research compliance. So the very opposite of what Pei Chao talked about, what Dr. Pollock talked about. I am, we certainly all have the same goal, but I work on the other side of this. If you don't know what research compliance is and didn't know that it was a job, you're not alone. I didn't either. Certainly not until I kind of found myself doing it. I've been really, really lucky over the past 10 to 15 years to be able to work with some really great researchers. The goal of research compliance is really to help our researchers conduct research in the best way possible. I don't think that we could have had a better segue than what Dr. Pollock gave us, so thank you. But Dr. Pollock talked a little bit already about laws and regulations and maybe the more boring side of research. But it is also an important side. One of the things that has really struck me over the years in my role as a research compliance professional is the myths that people have about research. And it's, I hear all kinds, Allison mentioned a couple of them. I think you're kind of alluded to a couple of them. Myths like, well, researchers don't care about me and they just care about their data. And all they care about is, getting good data, and they're willing to do anything to do that. And they're going to use my cells or use my information without telling me about it. And all of those things aren't true. I think we, can see already from what from our discussions with Pei Chao and with Dr. Pollock that researchers are really passionate about what they do, and they're passionate about the people who participate in research. So that's kind of what I wanted to talk about today. The problem with myths is that they're really powerful. And they're powerful because they're often based in fact. They are based in fact, but they become so far removed from time and context that they no longer reflect what really happened. And all that's left is kind of the fiction. They change, myths change as they're passed from person to person, as they change throughout time. It's kind of like playing the telephone game, right? Like something, the facts are the facts here, but by the time we get 50, 60 years down the road, it's a very different environment, and the truth looks very different. And some of those truths in our history can make it really difficult to trust what's happening today. I think we've seen this over the past year, especially during the pandemic. Luckily we've had some really amazing scientific breakthroughs over the past year. Getting vaccines approved just from a regulatory standpoint in the time that we've done it is really an amazing feat. But there's also been some kind of hesitancy about research and about the trials that we've done and that our scientists have done to get us here. And a lot of that hesitancy, like I said, comes from our past as a culture and as an American research community. Dr. Pollock talked a lot about Tyler Trent and his family and his willingness to offer his cells to science, to hope that children in the future, hope that we can cure these issues for children in the future. He had an opportunity to consent and share his science with the world and really leave a legacy. One of the I think most popular use of research with cells has been the story of Henrietta Lacks. And unfortunately, this story has become so popular and such a discussion point because Henrietta Lacks didn't have that opportunity. Her cells were used without her knowledge. It's important, I think, to understand the context, though, of that use and to understand how it differs from the way that research is done today. Dr. Pollock talked a little bit about, the connection between the clinicians and the researchers and how they cross those lines to make sure that good research can be done and that we can provide good treatment to our patients. When Henrietta Lacks was alive, there really wasn't a distinction at all between clinical care and research. Research wasn't thought of as the kind of scientific discipline that it's seen as today. It was not kind of a separate, it wasn't a separate kind of science. Instead, research was really wrapped up in clinical care. And things today, so that's a good example of why Henrietta Lacks wasn't given the opportunity to consent, is because no one at that time recognized research participants as research participants, because no one recognized research as what it is today. So there were a lot of differences between what happened with Henrietta Lacks and her experiences and what happened with Tyler Trent's experiences. Ethical conversations and expectations have really changed since that time. Dr. Pollock mentioned that these are highly regulated areas, and that's absolutely true. Today's researchers work really hard to make sure that research is conducted in a respectful way, and work really hard to make sure that our research participants know what they're doing and what they're giving and how their cells will be used in research. We have laws today that weren't even thought of in Henrietta Lacks's time. Those laws really didn't even start, people as a culture and a research community in America, we didn't start thinking about regulating research and talking about how we should treat research participants until really about 20 to 30 years later. So it took a long time for these ethical conversations to start. And that context looks really, really different today. Today, research is really about people, and ethical research is the standard and the norm. In addition to being passionate about their research participants and improving people's lives, our researchers also understand that they need people like Tyler Trent and the rest of our research participants in order to conduct good research. Research is really about people. It's about helping people. Certainly as we talked about, Tyler Trent has really left this legacy of providing some pathways toward a cure. And that's really amazing. Research is also about protecting people. There are entire groups who are dedicated to protecting our research participants and to making sure that our research participants have a good experience when they participate in research and when they give cells, to biobanks and things like that, so that researchers like Dr. Pollock can use them. So there are lots of people and processes in place today to help protect our research participants that really weren't in place, back in Henrietta Lacks's time. The reality of research today is that research can't be done without people like Tyler Trent, without people like you and me. I am not a researcher. I'm never going to be able to cure cancer. But what I can do is use my skills, use my legal skills to help researchers understand how research has to be conducted in today's context. One of those things, as Allison mentioned, is informed consent. Informed consent is one of the biggest tenets of research conduct today. It is absolutely a standard. And if you've ever participated in research, you know that it's much more than a, hey, do you want to give a sample of blood so that I can do research on it? It's a much more involved process. It's a regulatory, it's a process that's dictated by the regulations. The regulations require that certain information be given to you when you participate in research. So it's really important to understand that informed consent process really is about you and about the research participants. It's important when we participate in research that we ask questions during that informed consent process. The researchers have some information that they're required to give to you. They work closely with our institutional review boards, as Dr. Pollock mentioned, to come up with the information that those two groups think are most important to give to our research participants. But informed consent is really about what's important to that particular research participant when they are participating in research. So if you go to participate in a research study, it's really important to ask questions and think about what's important to you. What's important about research really changes depending on the research participant. Some people are really interested in privacy. Some people just want to know, how much time is this going to take? How much do I have to do to participate? Some people want to focus on the risks. That information will be given to you. And some people want to know more about what's going to happen every day as I participate in this research. So it's important to think about, it's important for us as potential research participants to think about what's important to us as we go into that process. And it's important for researchers to think about what they think is important to tell those research participants. The institutional review boards and the other research compliance professionals like me help make sure that those things are done appropriately and that research participants really have the opportunity to provide real informed consent the way that Tyler Trent did with Dr. Pollock's group. So those are my quick thoughts about research ethics. I could spend hours and days talking about this, So I look forward to hearing any of your questions. I didn't want to sit here and read regulations to you because I might be a legal nerd, but probably everyone else is you don't want to hear that. But I'm happy to talk about it.
You're telling me we're not going to read the CFR line for line to get through all of the Public Health Act?
I mean, if you want that, I can share.
Summer of 2019, I certainly was going line by line through the Public Health Act, but for different reasons. So maybe that will be one of our discussion points. I know we've already had a couple questions coming in for you about this informed consent and what that looks like, especially in the context of like Tyler Trent and inpatient donations. So be ready for those questions because they are rolling in. Thank you so much, Professor Waltz. Before we get into our Q&A, we want to give our audience, you guys watching, whether you're live streaming or here in the Zoom call, we want to give you the chance to win some prizes. Hope you were paying attention because we are going to get into a small trivia game. It's just a few questions, but we want to give, you know, although we're in this virtual format, we can still have fun. So you can see if you're on the Zoom call, you'll see, or I guess if you're live streaming, you'll have the URL, which is joinmyquiz.com/pro. You can do this on your phone, you can do it on your computer, your iPad if you're bougie. Go to joinmyquiz.com/pro and enter the code 713694. That is the code for our little trivia game. Similar to like Kahoot, if you have ever done a Kahoot, it's just a different platform. And yes, I did say prizes. So we will be shipping out to our winner of this trivia game a small prize from the Taste of Science crew. And we look forward to seeing how much you all learned from our previous three speakers. Although I will say, I looked through the questions, so I won't be participating, guys. There's no insider dealings going on. But I didn't know the answers to some of these questions. I learned putting these questions together, and I study cells like every day. So I feel like I maybe should do a better job at my job. But we're going to give everyone just a minute to join in on our trivia game at joinmyquiz.com/pro and enter the join code 713694. Look at that. Okay, we have a couple of participants who want to win prizes. Free things, prizes. I mean, come on. Who doesn't like a good prize, especially during the panini, the panorama? I am here for a good prize, for a good pick-me-up, especially on a day where, again, it is spring and snowing. Can you tell I'm not happy? I'm not pleased with a spring snow shower. That is not what I signed up for. I'm very envious of you, Pei Chao, and I agree. The snow, I would not miss the snow. I think if I left, and I know my little vegetable garden would not miss it either. My little peas would be very happy to not be in the snow. All right, the quiz is starting momentarily. Our first question, well, was answered, and we have a leader. Ooh, getting some wrong. Come on, y'all. This is going to be a tight race for these prizes. I don't know. Ooh, we might have to get some extra prizes going. So it looks like with just a small margin, we have a winner, John. Congratulations. We will reach out to you to get your information, send you a little Taste of Science prize to congratulate you. I know we still have one person filling out the quiz, filling out the trivia, but it looks like you are a clear winner. And we might have some follow-up prizes for number 2 or spot 2 and spot 3. So do not be surprised if you get a message from us asking for some shipping information. So thank you for participating in our little trivia game. And hopefully you learned something. I know I did. 200 different types of cells. What? That's crazy. And 30 trillion total in the human body. So there's 200 different types and then 30 trillion. And that doesn't include all the bacteria, which if you are a fan of South Park, you know that outnumbers your cells like 10 to 1 or something. There's a lot going on. There's a lot of cells that make up your body, and most of them aren't even you. They're mites, they're bacteria. I had no idea. That was a new fact for me. But thank you for everyone who participated. So for those of you who are in the top 4, so John, LM, PB, and, oh, it's showing, hello, John, PB, LM, send us your email addresses to the science. You can send it in the Zoom chat to the Scientist Inc., to the panelists. That would probably be easiest. So just do that here in Zoom chat. I promise we're not going to share it. We're not going to sell it. We do believe in data privacy here in Indiana, in Indianapolis. But in Zoom chat, send a message to the panelists with your email address, and we will go ahead and send out. We'll get your information from you. We'll send you an email, and we will get your prizes to you. So thank you for participating in our fun little trivia game, and I hope you learned something, because I know I did. Now we're going to get to our final piece of our event, which is a little panel discussion, a little Q&A with all 3 of our speakers. And so we really got to see the whole gamut of cell research. We got to see, Dr. Pei Chao showed us how you can build mini organoids, little inner ear organoids, using the cells as the building blocks. And then Dr. Pollock showed us a way that we can take cells from a person and use that to create a different type of model. So instead of using cells as the building block, we're using the cells as more of like the interventions, more of our variable. And then, Amy Waltz really gave us a great overview of how we can do that respectfully, and how we are not just walking through a Walmart trying to take people's samples and taking things from anybody who falls asleep. I'll take your DNA. It doesn't work like that. And so making sure that we're really seeing the whole gamut of cell research for what it is, from tiny organoids to, these whole systems of compliance, and really approaching research with respectfully, I think, is the way that, at least from the researcher side, we try to do it. So we got a lot of questions that came in. And I think this first question goes to Dr. Pollock, but I also would be curious to hear from Amy Waltz. So in the case of Tyler Trent, you talked about how his family was very involved. So maybe his case is an outlier, but how much say does his family have in the types of experiments that are performed using his cells? And then maybe, Amy, you can expand, when somebody gives, cells to be used for research, how much of a say do they have in like future experiments that are done?
Yeah, that's a great question. We actually discussed a lot about this case before the code was broken. So the way the whole situation happened is we get samples, we have a biobank that releases the sample to us, and then the code gets changed. And so we have our own coding system. And so there's only a couple of people who can link the codes, and they have, different layers of approval because of, HIPAA and all this kind of thing. So what happened to us is one day I'm in my office, and this is probably October 2018, I think. And one of my oncology colleagues called me on the phone and said, we have an interesting case here. We have a young man who, I think at that point he was maybe 18 and a half. And so he's no longer a minor. He has approached his family and said, what happened to that research tissue? And Tyler was just a very curious young man. And so the oncologist said, well, he went to the biobank and was like, well, looks like the Pollock group did receive some tissue. And again, that's part of the consent that Tyler fills out, that it's going for research. And the consents we have at Riley Hospital, they spell out what we will be doing in a general sense. And so it's pretty broad. I mean, it's we're not going to go selling his tissue or anything like that. We're using it for research purposes. And so it was pretty broad in terms of we could go in and look at the molecular signature, and we could develop our own models. And what we did in the follow-up, so once we looked at our logbook, we're like, yes, we actually have 2 of these models that made it all the way to being able to grow into the immunodeficient mice. And so the other thing we did, because this is unusual, we did engage the family. And it's kind of it was an interesting situation because this family was grieving for their son who they have lost. And we did everything we could to be very respectful about that relationship. And we let the family guide how much they wanted to know. Okay. We would give them opportunities. The RCF has folks that work there, Raleigh Children's Foundation, that are very good in working with these families. Also, Jamie Renbarger, she's the division chief at Raleigh. She knew the family, and so she could have conversations with them. And so we wanted to communicate as much as they wanted to know, and emotionally how much they wanted to know. And the Trent family is just one of those families. They're like, we want to know everything. So they actually came to the laboratory. they actually looked under the microscope. The cells you all saw, his mom and dad came in the lab and looked at that. And that's pretty brave. I don't know if I could do that. But they did that. They wanted to see where the tumor cells are stored. And we have a big like liquid nitrogen thing. And so we pulled it out and showed them. And so we kind of let them guide it, but we were very aware of making ourselves available and providing information that they needed. And it is a little bit of a dicey area because I think Amy made a great point nowadays. Here's the clinic and here's the research. And for a while, it was probably almost too separated, okay? That we'd be over here doing our thing. No, don't talk to the clinical folks, right? But now we're trying to have that bridge, and it's a ever-changing bridge, and how you have to handle it ethically. So this was a very different situation. We have a couple others now as well, but the vast majority of our patients, there's never any contact whatsoever. We don't know their name or anything.
Very interesting.
Yeah, Allison, I'll jump in too. I think I think Dr. Pollock is right. I think this is probably the exception. We do know of a few cases, both nationally and here at IU actually, where researchers do have a really close relationship with a donor family or with a donor. Henrietta Lack's family is now involved in discussions about how her cells are being used. After years of them, not being informed about what was happening. So that's a great step forward. But I think for the most part, research participants could certainly get that information if they wanted it. Researchers, in my experience, are happy to share. Everyone loves to talk about what they do, especially with people who are contributing to what they do. So I think researchers are always willing to talk about those things with research participants. But for the vast majority of participants, they're willing to donate their tissue or their cells to a biobank and then let the research happen as it will. Those consent forms do outline broadly what kind of research will be done. But for the most part, research participants, when they consent to a biobank, don't get to decide what types of research will be done. It's really just a decision of, here's what the researchers are saying, here's how they expect my cells to be used. Is that okay? Am I comfortable with that? But it generally doesn't get more specific than that.
Yeah, and so maybe a follow-up question for Amy. So in the case of Tyler Trent, that information was re-identified. Is that normal for patient samples?
So I think the norm is for them to be de-identified, at least at least for researchers to not have information not have access to those identifiers. But we do know of a couple of situations where research participants have come back and said, I have something else and I want to be involved. The Komen Bank, I know many people here in Indianapolis are familiar with the Komen Bank. They collect breast cancer samples. There are a couple, usually from healthy women. We do know of at least 2 or 3 research participants who have come back to that bank and said, I have since gotten breast cancer and I'd like to share my breast cancer tissues. And those participants have been re-identified at their own request. So it does happen, but certainly samples stay de-identified or anonymized for the vast majority of researchers.
That's fascinating. I as a researcher, I didn't know that there were so many patients who were willing and excited to be that involved in the research done with their samples. That's fascinating. Thank you for those thoughtful answers. Now we have a question for Dr. Pei Chao. So we have some listeners who are curious whether your inner ear research is potentially related to tinnitus or inner ear ringing, or maybe if another like inner ear disease.
Yeah, I think that's a lot of people have that kind of question when they know we are working on inner ear and then they want to know what can we really contribute to the human health. And then that's what we are doing now. What we are doing is the first step to understand like why people, for example, why people have the tenderness, like why you have ringing, because there's still a lot of uncertainty about what's the cause of that kind of symptom. And as I mentioned earlier, it's almost impossible to pop out a person's ear to figure it out because it will cause actual unnecessary damage. So what we are doing is using the culture to identify what the cause and then the mechanism underneath the problem we can see on the surface. And then from there, then we start tackle what will be the solution for that. So yes, we are toward that direction. Like all we are doing is trying to identify the cause of the inner ear disorder. So, and one of my funding agents called Hearing Health Foundation, they have a lot of information about how research can impact the day-to-day life. So I also encourage people can look it up if you are like, because I know a lot of people have like, if you like rock and roll, you probably had an issue with ringing ear, and then a lot of like people might have like age-related hearing loss, etc. And all those, it's like current direction of research is trying to, because that's one thing I did show, like hearing, and then here's they are irreversible damaged. So once they are damaged or degenerated, it's irreversible. So that's another reason why a lot of elderly people will start noticing having hearing loss or a balance sensing issue because they have some just nature degeneration in their inner ear. And then that's also one of very hot topic we try to figure out what we can do to regenerate or like repair the damaged tissue. And then those are like our goal for our research at the moment as well.
I was in a marching band for 10 years. So when you get an answer, I really need to be first on that email list, because I'm telling you, sitting next to a snare drum for 10 years was not good for my hearing. Thank you for that. I know there's a lot of people with tinnitus right now who are waiting with bated breath for your research. We have another question for Dr. Pollock about personalized medicine. So, you talked about how you're developing these animal models from patient-derived tumors, and it's a form of personalized medicine, but does personalized medicine help anybody else beyond the person who donates, or can that research be used to help others?
Yeah, it definitely can. So I'll give you one example that I think it's important for me to discuss just a little bit. So one reason we want to generate these models, of course, is we want to find the best treatment for that model. Now, it takes a long time for us to develop this model. So at that point, the information we're getting from that model may not apply to that patient it came from, okay? So that's the one thing I wanted to say. And it has a lot to do with, we get very limited tissue. The tissue can be highly necrotic, so we get a small piece. Actually, the second donation we got from Tyler, I really didn't even think it was going to grow. There was so much necrotic tissue in there, which is very common in this type of cancer. But one example that we have with the Tyler Trent case is there was one of the drugs that he was put on very late in his course, okay, of disease. And it's a drug called palbociclib, and it's actually a CDK4/6 inhibitor. You may have seen it on, there's ads for it, used in breast cancer all the time. And so part of his signature was that there was a hyperactivation of the CDK4/6 pathway. But by the time they got all that information, as I said, we didn't see, the program wasn't even developed when Tyler first came to Riley, but this was part of his signature. And so they put him on that inhibitor, but at that point, his disease was so progressed that I don't think it would have mattered what you put him on, frankly, because it had progressed. But what we were able to show in the laboratory is that with his tumor, we were able to show in the mouse model that the tumor responded very well to palbociclib. And this is a very important point because it provides rationale for early intervention. Okay, so there are going to be many more kids that are going to come along and they're going to say, hey, this case has a CDK4/6 hyperactivation event. You know, there is more and more rationale to put these kids on a CDK4/6 inhibitor like palbociclib early in the time point when the tumor burden is not big, when there aren't so many underlying, you know, conditions. So the personalized medicine, you know, we all want to have a magic bullet that you could use on every single cancer. And I'm a big proponent of still looking for those magic bullets, right? Because, you know, it takes a lot of money to develop drugs, takes a lot of money to run clinical trials. So it's kind of a mixture of that, but the models can provide rationale for so-called personalized therapy that can be used in other patients later as well.
Interesting. Yeah, I think the word personalized medicine is maybe a misnomer.
I think it is a little bit. I think it's personalized to a point. And you know, one thing I believe that's going to happen is that you're probably going to have like one group of drugs, there are a lot already out there, that you're going to use across many cancers, like anti-angiogenesis type drugs, PI3 kinase inhibitors, and then you're going to build the personalized part on top of that. So, I mean, frankly, I would like to be a proponent of finding these magic bullets. It would certainly help a lot. So, because these drugs are very expensive. And my colleagues over in the clinic spend a lot of time dealing with insurance companies trying to get these things paid for. So it's a big, and that's another thing I actually wanted to say really quick about working with the oncologist. They help us prioritize the questions we're going to ask. Because as a PhD, I may be like, hey, let's try, you know, this drug and that. And they'd be like, Karen, don't do that. We don't care about that. This is what we care about. And so they actually help us prioritize even what we're going to study.
I completely agree. That's been one of the best, I know, for me in my research, working with clinicians. It's you come up with all the questions and they tell you what's most important in the clinic and really get that bench to bedside going.
Exactly. Yeah.
So thank you for giving us a little insight into the future of what's already a cutting edge technology, precision medicine. Knowing that people like you are at the forefront of this movement and of this technology is comforting for me. And I bet for all Hoosiers out there.
We learn every day. That's one thing you do. You have to learn lots of different signaling pathways that we didn't know anything about. So it's fun. You're constantly learning.
Learning is always fun.
Yeah.
So speaking of the future of the fields, Pei Chao, you talked about how this group at IU has developed this new inner ear organoid and being able to use cells in a completely different way to develop these 3D mini organs in a dish. So what do you see the future of these organoids being used? Like, how do you think that they'll be applied in the future? Will it be for ear disease? Will it be for development? Do you think you'll be able to test drugs, you know, for maybe this hair growth in the inner ear? What do you think is the future of that field?
Well, basically everything you say, we can see it coming, to be honest. Like for example, drug screening. The inner ear organoid will be a good tool to have it because, you know, inner ear is very small tissue and then there are very limited biological material. So if we can really master the organoid system, then we can provide enough hair cell for high throughput screening, then we can figure out what might be possible good drug to deal with like hearing loss or vertigo or sensing. And then also, we also trying to provide, from understanding the developmental aspect, we can understand what stage might be the best candidate to put into the inner ear as cell therapy. Because if you just put the stem cell in, it's going to go crazy. It's not going to go into inner ear because there's so much potency there. So those things, it's the combination about we can use this system to not only directly jump in applicable medicine, but we answer some very fundamental question which has been lingered around for a long time because just such fine tissue and such limited resources to study. So I can see once that's another reason I'm doing the developmental study, because once we learn more about how they can develop to the inner ear, we can use this knowledge to go back to optimize the organoid system to make it have more potential to do further drug screening, stem cell therapy, and then learn more about what's this unique cell, how they function, how the physiology inside of ear. So yeah, like I think there's a really wide door open for this stem cell organoid system. And I think a lot of groups, they learn this from IU's research team, which I think is very impressive. Like originally I jumped in the Indiana University because I think this research is amazing and has high potential. And then now a lot of research groups all over the nation, even all over the world, think there is a potential in this system. And then I think everybody is trying to push this relatively new, which only like 5 years last system to become more feasible tool for more groups. So yeah, I think there is like so much we can do with that, and I'm looking forward to keep doing that until I cannot do it anymore.
Yeah, well, that's good to hear. I know those of us with hearing loss, or at least the beginnings of hearing loss, are very comforted knowing that you're at the bench working to help us. And that's, you bring up a great point too about stem cells. I know as my mom has grown older, she's always joked that she's gonna take stem cells. And they joke about this in popular media. Oh, I'll take stem cells from umbilical cords and I'll inject them and I'll be young again. And that's not really how stem cells work. They're so finicky and complex. And if it was that easy, they'd be growing on walls. And it just is not the case with stem cells. So you bring up a great point about how stem cell research is really complex, and it's not just inject a cell and everything will go great and it'll reverse, because if we could reverse aging and reverse time, well, we wouldn't be sitting here on Zoom. I'd be telling you that right now. We'd be in Jetsons cars flying and be in our little Wally chairs.
Yeah, I think there is some misconception just because stem cell is like used widely to convince you certain unrealistic dream. There is hope, but I think there is a lot of steps between we can have a couple of stem cell and then suddenly back to 15, that kind of situation.
Maybe go post high school, go a little past the teenage year. We'll go mid-20s. Does it sound good for everybody? Let's get our stem cells there. Let's get them all in the same, get them all on track. So as we close out our event, I have one last question, and maybe controversial for Amy Waltz, not to put you on the spot, but one of our listeners is curious if you can think of any research practices or maybe something in research compliance that's currently in use that you may see being in the future deemed unethical, or maybe something in research compliance that you see might change you can see in the near future.
That's a great question. So one of the things that has been really controversial with the COVID vaccine has been these challenge trials, where participants are actually given the vaccine and then treated. Just saying it sounds controversial, right? It makes you go, ooh, we shouldn't be doing that. Because those kinds of trials, we've seen that kind of thing go very badly in the past from an ethical standpoint. That doesn't mean that there isn't a way to do it ethically. There are a couple of trials like that, not here in the US, a couple of, especially in the UK, and they're being reviewed by ethical boards as well. So, there are some ways to use careful informed consent and things like that to get to address some of those ethical questions, but that's one of the things that I think has been really controversial over the past year. And I think we're going to see quite a bit more discussion, especially as we learn the long-term effects of COVID, especially. So I think this is going to be a little bit of an ongoing conversation in the research ethics world.
For sure. Well, I think everything COVID related is going to be a long going discussion, but especially, yeah, when it comes to even just research design, COVID has really opened up a lot of discussions. And so that's interesting that the compliance world is also looking at COVID trials under maybe a little stricter of a microscope. And moving forward, I think we're going to see a lot of changes in the way science is done and the way clinical science is done. So that'll be very interesting to hear from you in your office in the near future. I will be looking on the IU Research Integrity Research Compliance blog page, which I'm not saying you talk about being a legal nerd. I keep up with that blog. So I will be looking for your next publications. So with that, we come to the end of our event. I do want to give the biggest thanks and the biggest shout out to you, Professor Waltz, Dr. Pollock, Dr. Pei Chao. You guys have been wonderful and really highlighting not just Indianapolis for the nationwide Taste of Science world that this is going to be broadcast and viewed by, but even here, just to hear about the people who are working a few offices down from some of us. You're our neighbors. Part of our goal with this event is to highlight the fact that we have so many incredible academics here in Indianapolis and in Indiana. But we're also just your neighbors. We're normal people too. And the ivory tower is no longer a Rapunzel tower. It's just, down the street, kind of, around the block kind of place. And we so appreciate your time and your willingness to come talk about these really complex and, wildly complex concepts and ideas in your world and bring them down to a level that I can be, 1 or 2 beers in and still get something out of it. And understand it. So we thank you so much for your time and for your expertise. I want to give a big shout out to the Taste of Science Indianapolis team, the CINSO team, Indiana Sciences. You all have been wonderful behind the scenes organizing this event. This event will be recorded and put on YouTube for your future viewing pleasure if you would like, or if you would like to reference it in the future. If you would like to donate to the Taste of Science cause for when we can go back to in person and actually give you guys beers, because normally we would be all giving out beers because Indiana is known for the 3 C's: corn, cars, and craft beer. So we would normally be sharing some beverages with you. But if you'd like to donate, go to tasteofscience.org and you're free to donate to our nonprofit science communication cause. Or if you'd like to keep it local, go to indianasciences.org, where you can find out about some of our upcoming events, and you can even buy some cool Indiana-themed masks and sweaters. And I wish I wasn't telling you to buy a sweater in April, but holy cow, it's snowing in Indiana, because that's just where we're at. So with that, I'd like to thank you all for your attention. Thank you so much for coming, and I hope you enjoy the rest of your week and your evening. With that, I will see you all later. Ta-ta.
Bye.
Bye, all.